Today we're going to be talking about graphing rational functions, and we're going to do a quick review real quick for your bell work of identifying the asymptotes, the holes, the x-intercepts of a function. So given that you have g of x equals x squared minus 5x plus 6 over x squared plus 4, go ahead and see, can you identify the horizontal asymptote, the vertical asymptote, the slant asymptote, and the x-intercepts, if there are any. Now, again, they're not going to have all of those things all the time. Remember, your vertical asymptotes are determined from the bottom. So, where does the bottom equal 0 to where you have to exclude it? And in this case right here, you cannot factor that. So this one, there is no number that I could plug in that would give my bottom to be 0. So as far as a vertical asymptote goes, I don't have any. A horizontal asymptote is determined by the leading coefficients of the top and the bottom. So if you notice, both powers, top and bottom, are squares. This means that I have a vertical asymptote at x squared over x squared. Now, my coefficients are 1 over 1. So that means that my asymptote is going to be at 1. Y equals 1. Remember, they're always equations, so we need to make sure we write them as equations. So I have a horizontal asymptote at y equals 1. And then as far as slant asymptote goes, remember, if the power on top is greater than the power on the bottom, I have a slant asymptote. And so it's not true. If I have horizontal asymptotes, I'm probably not going to have slant ones. And then the x-intercepts are determined by factoring the top and setting it equal to 0. So if I take x squared minus 5x plus 6 and set it equal to 0 and solve, what are the factors of 6 that add to negative 5? And that is going to be x minus 3 and x minus 2. So I have two x-intercepts at x equals 3 and x equals 2. And so there is the answer to that problem. Now moving on, we're going to be talking about graphing the rational functions that, yes, last time we talked about when we found everything for the graph. So we're actually just going to be putting that into practice by actually graphing it today. So don't forget the things that we've already talked about. You know, vertical asymptotes, what those are. Holes in our graph are found by canceling the factors. So it would be where an asymptote would exist, except for the fact that we can cancel it out. And then our horizontal asymptotes, if the degree of the numerator is larger than the degree in the denominator, then there are no horizontal asymptotes. We're going to have a slant asymptote in that case. If the degree of the numerator is smaller, then it's at 0. And if the degrees are equal, then that's where we take the leading coefficients and just divide them. And then today we're going to be focusing on oblique, how to find oblique or slant asymptotes. So we didn't talk a whole lot about them. We included them last time, but we didn't really discuss on how to find them. And so this first example that we're going to do is actually just find the oblique asymptote or slant asymptote. Okay, so first off, let me give you a picture of what a slant asymptote would look like. So let's say that we have a graph like that. A slant asymptote is just going to be a slanted asymptote. So, you know, we've got vertical asymptotes, and then we've got horizontal asymptotes. The slant asymptote is just an equation of a line that's an asymptote. And so we're going to actually use long division to find that. So if I'm going to write down x squared minus 2x plus 11 divided by x plus 3. So what you're going to do is look at the first terms only. What do I need to multiply x by to make him look like x squared? And that is an x. So then you multiply it, you distribute back through. So that's going to give me x squared plus 3x. Change your signs. So this is now negative. This is now negative. And add down. Those are going to cancel. And this is going to give me negative 5x plus 11. So then look at your first terms again. Again, I have x, and I want him to look like negative 5x. So I'm going to multiply by negative 5. And again, distribute that negative 5 back through. So this gives me negative 5x minus 15. And change your signs. So that's now plus, and that's now plus. And add down. Those cancel. And this gives me 26. Now, when we're finding oblique asymptotes, the only thing that we care about is that equation right there. We do not care about the remainder. So you're not going to include your remainder. So our equation for the oblique asymptote, and remember, it's always an equation, so make sure that you include y equals. If you just write x minus 5 without the equation part, that doesn't make any sense, because this is telling me it's an equation for a line. So if I were to graph the line y equals x minus 5, it would look like this, sort of. So that would be my oblique asymptote, slant asymptote. On example 2, it tells us to sketch the graph of the rational function by hand. So we're going to have to check for intercepts, vertical asymptotes, horizontal asymptotes, holes in our graph if we have any, and just make sure we cover all of our bases before we try to graph it. So first thing I'm going to do is I'm going to start by trying to identify my asymptotes. So I'm going to write horizontal asymptote, vertical asymptote, oblique asymptote, and then my x-intercepts down here. All of these things are going to help us graph this. So first off, remember your vertical asymptotes are where you have zeros on the bottom. So what I'm going to do is I'm going to factor that. That is a difference of squares. X minus 2, x plus 2. So I actually have two vertical asymptotes at x equals 2 and x equals negative 2. So if I put those on my graph, I'm going to go ahead and graph my two vertical asymptotes. There's x equals negative 2, and there is x equals 2. Now what I'm going to do is see if I have any horizontal or oblique asymptotes. So if you notice the powers, my powers are equal on top and bottom. I have 2 and 2. So what I'm going to do, that means I have a horizontal asymptote. So you take the coefficients in front and divide them. 1. So I have a horizontal asymptote at y equals 1. So I'm going to go ahead and graph that one as well. Now, remember, asymptotes, you generally don't cross an asymptote. An asymptote is kind of like a barrier. You're not generally going to cross the barrier. You definitely never cross vertical asymptote barriers. Sometimes in special cases you will cross horizontal asymptotes. But that is something that you learn in calculus. All you need to know is that sometimes you will cross a horizontal asymptote. It's not like a solid barrier like a vertical asymptote is. We do not have any oblique asymptotes because that would need my power on top would need to be bigger than my power on bottom, and it's not. But now I'm going to find my x-intercepts so that I can graph this. So if you look, I'm going to factor the top because that is going to give me my x-intercepts. Set it equal to 0. X, my factors of 4 that add to -5. So -4 and -1. So I've got 2 x-intercepts at 4 and at 1. So x equals 4 and 1. So what I'm going to do is I'm going to go ahead and put those on my graph. So here is 4 and here is 1. Now, always, 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 you can double check yourself on your calculator. So I would recommend getting your calculator out, your graphing calculator out, and plugging it in. Just remember, make sure that you use parentheses when you put in the top. So in your calculator, it would need to look like, y equals, make sure you put that in the top, and then put parentheses around your bottom so that it will graph it correctly. So double check yourself, and when you do that, you'll notice this is kind of what your graph will look like. And again, like we just talked about, right there we cross that horizontal asymptote, and that's okay. You just don't have the knowledge yet to understand until you get to calculus exactly why that happens. Just know you've double checked yourself on your calculator and that's what it looks like. Now notice we don't have any holes on this one because when we factored the top, we got x minus 4 times x minus 1, and when we factored the bottom, we got x minus 2 and x plus 2. None of those canceled, so that did not create any holes for us. On our next graph, on example B, we are going to experience a hole. So let's go ahead and jump down there. Okay, so if I were to factor the top here, I notice I have an x squared in common. So I'm going to pull that to the front, and that's going to leave me with x minus 1. Now on the bottom, I have an x squared. So what do you notice is going to happen here? My x squares are going to cancel. So where I would have had a vertical asymptote at 0, now I just have a hole. So it's going to be, I do not have any asymptotes, so let's write that down. None. X-intercepts, you still need to find those. So again, once we have our top factored, and you're not going to include this, we're going to set that equal to 0, and I have an x-intercept at 1. So I'm going to go ahead and I'm going to put that on my graph, that I have an x-intercept at 1. Now, because these two terms canceled out, this is essentially what my graph is going to look like. So, which is just a line. However, remember, we do have a hole at 0. So, when we're graphing this, we're going to have a hole there. And that's what it's going to look like. Now on to the word problem. So, reading this, it says a 1,000 liter tank contains 50 liters of a 25% brine solution. You add X liters of a 75% brine solution to the tank. Show that the concentration C, the ratio of brine to the total solution of the final mixture, is given by the equation C equals 3x plus 50 over 4 times x plus 50. So what it is asking for on part A is for us to prove that when we set up the problem that we can get to this equation. And that's what we're going to do. So let's set up. So reading the problem, if I have 50 liters at 25%, and then I'm adding some unknown amount of liters with a 75% mixture to equal C, which is the concentration, times my my liters, 50 plus X. So that is the equation set up. My goal is to prove that I can get to there. Okay, so what I'm going to do is multiply 50 times 0.25 is 12.5 plus 0.75x equals C times 50 plus x. Okay, so what we're going to do is we're going to divide out the 50 plus x because this equation is solved for C. So I want to solve my equation for C. I'm going to do that by dividing out 50 plus x. 50 plus x. So that gets C by itself. So what I have is I have C equals 12.5 plus 0.75x over 50 plus x. So what I'm going to do is I'm going to compare now. I'm going to look at this equation and compare it to mine and see, okay, what's the difference here? So I'm going to look at the bottom because the bottoms, they both have an x plus 50. What's the only thing that this equation has that this one doesn't? And that would be a 4. So if I end up multiplying both the top and the bottom by 4, then that is going to give me the exact equation that's been given here. So that's the last step, is that we're just going to multiply the equation by 4. And when I do that, I get 3x plus 50 on top. And I get 4 times x plus 50 on the bottom. And now you have made them, you have proved that when we set up the problem initially and we solve it out, that we are getting the function that they give us. So it says now on part B, determine the domain of the function based on the physical constraints of the problem. So let's look back in the problem to figure out our domain, because the domain is going to be the x values. Domain in this problem is the liters. So notice we start off with a 1,000-liter tank, and it already has 50 liters in it, which means as far as my domain for this function goes, I need to figure out like how far I can take my liters before I'm at capacity at 1,000 liters. So my domain is going to be obviously going to be all the values that are greater than or equal to 0, but are also less than or equal to 1,000 liters minus the 50 that are already in there, or 950. So how you write that will be 0 is less than or equal to x, is less than or equal to 950. That's how we're going to get the domain. So I can fill it up anywhere between 0 and 950 liters before I reach my capacity. Now, use a graphing utility, so you'll want to get your calculator out and plug this function into y equals. Make sure that you use parentheses around the top and that you use parentheses around the bottom. If you don't do that, it's going to give you an incorrect graph. And so from this graph, we're going to look and see what it says. Now you'll want to change your window probably to where you see 0, your x min is 0, and your x max is going to be 1,000 or 950, either one. Your y min is going to be 0, and your y max you'll want to make 1. When you do that, it's going to give you an xy axis like this. Here is 0 and here is 1. Now why do I want to use 1? Well, remember, in percentages, 0% to 100%. So decimal wise, that is 0 all the way up to 1. That's why we use 0 to 1 here. We're representing, this is our percentage, anywhere from 0 to 100%. And then 0 to 950. Now notice your graph looks somewhat like this. Now, what it says is, as the tank is filled, what happens to the rate at which the concentration of brine increases? What percent does the concentration of brine appear to approach? So what we're going to do here is figure out, as the tank is filled up, what happens to my rate of concentration? Well, I'm adding a 75% mixture to 25%. So eventually, over time, I'm going to get closer and closer and closer to what percentage? 75%. So if you notice, my rate of concentration slows down. And it's eventually going to cap off at what number? And that's going to be 75%. Now, how can you tell that algebraically? Well, remember, asymptote-wise, we've got a y asymptote at 0.75. How did I get that number? If you look here at your original equation, remember, you take the highest powers of both top and bottom. So 3x over 4x. So 3x over 4x. And because my exponents match, remember, you just take the coefficients in front, 3/4 equals 0.75, and that's how you tell what the asymptote is. My y asymptote is, it's going to approach 75%. And that takes care of graphing our rational functions.